So let's go ahead and get started. So we're going to start in 5.1. This is actually where you probably ended your Calc 1 course, or at least hopefully this is where you ended your Calc 1 course. If not, I'm going to cover it in its entirety again, talking about U substitution. So let's look at an example of a U substitution. So say you wanted to take the integral of e to the x over 1 plus e to the x dx. As it's written, that integral is not very obvious or easy. But we can pick something that, when I take its derivative, is in the problem itself. So for example, could you find something that if I was to take the derivative of it, I would get back something else in the problem? E to the x, yes, but also that 1 plus needs to be with it. Because what's the derivative of 1 plus e to the x? It's just e to the x. And then I'm going to put dx out there at the end. Let me kind of remind you where that comes from. Remember, that's du dx, right? The derivative of u with respect to x is the way we say that. And then I can think about taking that dx and multiplying it to the other side, so that I have du equals e to the x dx. Well, look there. There's e to the x dx, which is my du, right? And then that 1 plus e to the x is u. So this actually, by u substitution, gets replaced, or we change it to be 1 over u du. What is the integral of 1 over u? That's the ln of u, well, absolute value of u, plus c. And then all I have to do now is plug that u that I substituted back in. And that would be the function. That would be the antiderivative. That's what I was looking for. Now, I don't expect you to do this, but if you wanted to check your answer to this problem, you could take the derivative of this and see if you get back the original integrand. Because if this is the true antiderivative, then the derivative of this would have been the integrand, the thing beside the integral symbol. Let's look at another example. What about the integral of the tangent of x dx? Do we know what the integral of tangent x is from our table or from our list of derivatives from Wednesday? Is that a special one? Yeah? What's the integral of tangent?
Isn't it like secant squared?
That's the derivative of tangent. The derivative of tangent is secant squared. What's the integral of tangent? Nope. The secant tangent is the derivative of secant. Oh, there you go. Well, it's negative natural log. It's negative natural log of the absolute value of cosine. So where the heck does that come from, right? It's not one that's obvious. So if we rewrote tangent as sine of x over cosine of x, if I take the derivative of one of those, I get the other. So if I take the derivative of sine, I get cosine, but the problem is cosine's in the denominator. But if I take the derivative of cosine, I get negative sine, and I would have negative sine and maybe a dx. So let's do that. Let u be cosine of x. Then du is going to be negative sine of x dx. Now I'm looking at my problem and I see that I have sine x dx, not negative sine x dx. So what I do what I like to do is I'm going to move that negative here over there and make that negative du equals sine of x dx. So I'm going to replace sine x dx with negative du, and then I'm going to replace cosine of x with u. So this becomes the integral of negative du over u. Yes?
Didn't you pull the negative outside?
Yes. So the next thing we might want to do, after we get that substitution in, and I'll go ahead and say this was by u sub. You are not contractually required to write u sub over the equals. I just want you to know, like, we can do this because it's a u substitution. I guess I'm the teacher. I should show all my steps, right? So he's absolutely correct. So we've got the integral, pull the negative on the outside, and I can rewrite this as 1 over u du, which, again, the integral of 1 over u is the natural log, absolute value of u, plus c. But the u that we picked was cosine of x. Not a special formula that we learned probably in Calc 1 or memorized. Somebody learned it apparently, but not one that you were expected to have memorized, because you can derive it using u substitution. Any questions so far? All right. What about x over the square root of 3x squared plus 1 dx? What would be something that you could pick that when you take its derivative, we could maybe somehow force it to be in the problem? 3x squared plus 1. Beautiful. You'd be like, wait. The derivative of 3x squared plus 1 is 6x. I don't have a 6x in there, right? So I do have, however, x dx, right? So here's x dx. I like to think about moving that 6 over, having du over 6 equals x dx. So I'm going to replace x dx with du over 6. So that's going to be the integral of 1 over 6, and I'm going to put a du right there. And then I'm replacing 3x squared plus 1 with u, so that's the square root of u. I'm going to pretty this up a little. I'm going to bring that 1/6 out to the front so that I'm only looking at the square root of u du, or 1 over the square root of u du. Now, I don't know about you, but like, I don't have all these little bitty integrals memorized. If you do, more power to you. I got a lot of cubbies up in my brain, and they're starting to get filled as I get older. So what I do is I convert those things like 1 over the square root of u to a fractional exponent. So I rewrite this as 1/6 the integral of, well, 1 over the square root of u becomes u to what power? Negative 1/2, right? So when I go and use the power rule on this integral, I add 1 to the top. So that's going to give me u to the 1/2, and then divide by 1/2, which is the same thing as what? Multiplying by 2, right? So that gives me 1/3 the square root of, and then we picked 3x squared plus 1. What's a question you might have? Ask me something. Nothing? Okay. What about the integral of cosine of x times sine of x to the 7th power? Maybe I don't need such a big integral symbol. What do you think here? What u would you pick? You want u to be sine of x? So that forces du to be cosine of x dx. Well, that's great because I have that. So this integral under the u substitution is going to be something du. What does it change to? What du? U to the 7th, they said. So this gives me 1/8 u to the 8th plus c, which I now, by resubbing back in, gives me 1/8 sine to the 8th power of x plus c. Pretty nice, right? Not too bad. All right, so we're kind of like a snowball. Like, I hope those were nice, it's, you know, like manageable. All right, but we're going to start letting the snowball kind of ride down a hill now. So these are going to get a little bit longer. We're going to do some more tricks. And then the last problem takes about a page to do. So let's get to it. So let's look at the integral of sine of x over 1 plus cosine squared x dx. So let's say that this pops up on your test. What would be the first place you would start to tackle this? So, okay, I'm going to put it in red for don't do this. But it's okay if you said it, because this is the time where we can make mistakes and figure out why it was wrong. So u equals 1 plus cosine squared x. All right, let's say we picked that one, and I took the derivative. Well, the derivative of 1 goes away, and then the derivative of cosine squared x is actually a power rule and a chain rule all wrapped into one. Do you agree with that statement? I don't care if you don't. It's right. It's the chain rule and the power rule all wrapped up into one problem. Because the 2 comes out to the front. The cosine of x was on the inside of the squared term. And then you take the derivative of cosine, which was negative sine of x. Now, in my problem, is there anywhere that has 2 cosine sine? No. And you might, wait. I took trig. There's some trig identities, right? So maybe you want to write this as 2 sine of 2x, right? Because that's a double angle identity. Is that anywhere in the problem? No. So we went on a rabbit hole to get nowhere. So somebody pick something else. Huh? Let's see if she picked a good one. Obviously she did. I didn't change colors. So du is equal to, the derivative of cosine is negative sine of x. Well, I look and I'm like, well, I got sine of x dx. That's pretty close. I'm just off by a what? A negative. But if I move that over, then I say, well, let negative du equal sine of x dx. Then under u substitution, this becomes negative the integral of 1 over 1 plus u squared du. Yes, no, maybe? I picked up that negative from the derivative. Well, what's the integral of 1 over 1 plus u squared du? Huh? Arctangent. That's a special one. It's my favorite. I'm telling you, you will see that many times this semester. Arctangent's my favorite. I don't know why. So that's negative arctangent of u plus c. But remember, u was cosine, so that's negative arctangent of cosine of x plus c. So I've had students in the past, they'll be like, wait, Mr. Smith, can I write this as tangent inverse of cosine x plus c? And the answer is absolutely. I don't care. I don't like that notation personally, but we all have our personal opinions about things, and my mathematical opinion is that is terrible notation. But anyway, that's why when I write inverse trig functions, I will always write arctan, arcsine, arccosine. But if you want to write the little -1, whatever floats your boat. Just know that deep down inside, I don't like it. If that'll persuade you anyway. Any questions? Any thoughts? Anybody learned anything new yet? Learn something new every day, right? You're supposed to learn something new every day. All right. So again, I told you we're kind of snowballing, so this is a little bit more difficult one. Ones like this actually have a special name. These are called U sub back sub problems. Or that's what when I learned them, that's what they were called, was U sub back sub. So you're still going to do a U substitution, but then you're going to sub that back in and end up solving another problem almost, it seems, entirely. All right. I'm just going to tell you the best U to pick, and it's the one under the radical. If you see something like this, the best one to pick is the something under the radical. So in this case, pick U to be 1 minus 3y. And don't take the derivative. That's why this one's weird. So I'm not finding du yet. What I'm going to do is I'm going to move everything and get y by itself. Because really, my goal is to get rid of that y and put u in there somewhere. I know it sounds weird and stupid, but I promise it makes life easier for us algebraically. So I'm going to move it over. So I'm going to do subtract 1, divide by -3. So I'm going to have u minus 1 over -3 is equal to y. Now I'm going to take the derivative of this. So dy is going to be -1/3 du. I'm going to let that sit there for a second because I want you to let that sink in. I took the derivative of both sides, right? So the derivative of y is dy. The derivative of u is du, right? But that -1 over -3, like that's the same thing as saying, like, if I wanted to rewrite this, I can write that as -1/3 u plus 1/3. Do you agree with that? And so the derivative of that is really just -1/3, but then we're differentiating with respect to u, so it's u becomes du. So we get this as what we want for our substitution. So under this u sub back sub thing, y now is going to become u minus 1 over negative 3. And the thing under the radical is going to become u. Come on. And then dy, notice dy is negative 1/3 du. So that's negative 1/3 du. So what I have effectively done is changed all my y's to u's. And you're like, well, God, that don't look like it made anything any better, right? You should probably naturally think that right now. But it actually does. Because you've got, let me do some highlighting here. You've got these two constants that when you multiply them together gives you a ninth, right? And I can factor that out to the very front. So I'm going to have 1/9 the integral of u minus 1 times the square root of u du. Now look how pretty that is, in my opinion. Now, why is that fantastic? Well, what's u times the square root of u simplify to? Any idea? If you were to add their exponents together, you would get u to the what? Huh? 3 halves. 1 plus 1/2 is 3 halves, right? Minus 1 times the square root of u, but the square root of u is the same thing as u to the 1/2. How easy is it now to integrate that? Like pretty easy, right? So I'm going to get 1/9, and then in parentheses, 2/5 u to the 5 halves minus 2/3 u to the 3 halves plus c. And then my last step is to plug my original u back in. So I get 1/9 times 2/5, 1 minus 3y to the 5 halves minus 2/3 times 1 minus 3y raised to the 3 halves plus c. You feel your snowball getting a little bigger? Ask me a question. Yes?
So in this problem, we're looking for in problems like this, we always be looking for 3 pieces,
Looking for 3 pieces.
like a u, and then because we found like a u
Yep.
to plug in, and then we found a dy, and then we found a y.
Yes.
We always be looking for about 3
Yes.
pieces,
If you got this,
something to look for.
yeah, so the main setup of problems that require a u sub back sub is where you've got like this linear piece. See, this y is linear, right? And you've got this other linear piece underneath a radical. Because those two don't combine nicely. But we forced it to where we get something that does combine nicely. And that was the power of the u sub back sub. It takes it from something that doesn't combine and integrate easily to something that does.
Are they always linear?
Are they always linear? I can't say with certainty that they're always. I mean, there's infinitely many problems in existence. We'll just say for the ones in this class, yes. You'll see them as linear problems like that for u sub back sub. It is my personal policy to never overgeneralize anything. Otherwise, every person who shops at Walmart is crazy. Present company included. All right, so here's our big snowball problem. It's an alpha. So that's the Greek letter alpha. So I like to change up variables because I get tired of using x all the time. So sometimes I'll use z. If I do trig functions, I'll use theta. I just wanted to throw in a Greek letter. Plus, the one on your lab I'm going to give you today is alpha. So I figured, let me model exactly what I want from you in your notes. Now, I looked at this for the first time when I was doing these problems, and I was like, I don't know where, because like we're going to learn a lot of techniques in this course, how to integrate stuff, and I was like, well, it's in section 5.1, so it has to be a u substitution. Well, what on earth would I use to do a u substitution? Because if I take the derivative of like the square root of alpha, then you get negative 1 over 2 square root of alpha, which is nowhere in the integrand, right? And then I thought, well, maybe, just maybe, it's a u sub back sub. And it is. So we're going to use that u sub back sub to find this definite integral. So what do you think, and it's okay, I'll tell you if you're wrong, we should use for u? Yep. 8 minus the square root of alpha. And just like we did in the previous problem, the first thing I solved for was what? Last time it was y. In this case, it's going to be alpha. So I'm going to solve for alpha. So if I do that, I get 8 minus u quantity squared equals alpha. Look at all that algebra. Isn't it great? So then I need to figure out, all right, well, what's d alpha? Well, d alpha is the derivative of the left-hand side with respect to u. So that's a chain rule, right? So that's going to be negative 2, 8 minus u du. Where'd the negative come from? It come from the derivative of 8 minus u on the inside, right? The derivative of 8 minus u is negative 1. So that goes to the outside with that 2. And the 2 came from the power rule, right? Bring the 2 down to the front, subtract 1, multiply by the derivative of the inside, which is where that negative comes from. So watch what happens. By u substitution, I get the integral from x equals 0, x equals 4, and this is going to become negative 2, 8 minus u, square root of u, du. Because d alpha, let me use that blue I was using, d alpha is that right there. Again, let's clean this up. The negative 2 can come out front. So we get 8 minus u times the square root of u. I thought I had do not disturb on. I do. All right, so let's look at that. That's negative 2 integral of x equals 0, x equals 4 times 8 times the square root of u minus u to the 3 halves du. Yes, no, maybe? Yeah? Maybe I change this, make it 1/2. So we have a bunch of fractional exponents. So keeping that negative 2 out there, let's integrate the inside. Well, the integral of u to the 1/2 is 2u, or sorry, no, it's 2/3 u to the 3 halves. So that's really just going to become 16/3 u to the 3 halves minus, and then the integral of u to the 3 halves is 2/5 u to the 5 halves, x equals 0, x equals 4. Why do I keep writing x equals x equals? Right, Because I'm using u now. Oh, dang it, you're right. I got all the way through there. Those should have been alphas. There we go. Should have been alphas all the way down. That's what I get for changing variables. So here there's two things you could do. You could either go back and substitute what you had for u into this expression now, and then plug 4 into that. And I don't know about you, but God, that sounds awful. Or we can now take what we have for alpha and plug it into our u. Because remember, u of alpha is equal to 8 minus the square root of alpha. So u of 0 is going to be 8 minus 0, which is 8. And then u of 4 is going to be 8 minus the square root of 4, which is 6. You see what I'm doing? I'm changing from x equals alphas to u's. So I don't have to like plug all that junk back in. I can just plug in numbers and keep going. So now this expression, negative 2, becomes 16, 3, u to the 3 halves minus 2 fifths u to the 5 halves, evaluated from u equals, and alpha equals 0 converts to u equals 8, and then u equals 6. I'm changing my variables so that everything matches now. All right, we got to stop for a second. And I'm sure you're like, thank the goodness. We got to stop. Not that we've done something wrong. But what's those bounds of the fundamental theorem? U equals 8 and U equals 6. What's off about those?
The bigger ones on the bottom.
The bigger ones on, you said the lower ones on top, bigger ones on the bottom, right? That's the problem. There's this special thing about integrals and the fundamental theorem of calculus that if I switch them, what happens?
When you add a negative.
You add a negative, but really we say that it flips the sign, or it negates whatever's there. So I'm going to do that. So now this is going to become, instead of negative 2 on the very outside, I'm going to make it a positive 2. And have 16 thirds u to the 3 halves minus 2 fifths u to the 5 halves. And now I can write this as u equals 6 and u equals 8. So I want to change those bounds so that the smaller one's on top and the bigger one's on bottom. Now, this is not pretty. Like, the answer to this is some awful irrational number. So we would just write this as 2 times 16 thirds times 8 to the 3 halves minus 2 fifths times 8 to the 5 halves minus 16 thirds times 6 to the 3 halves minus 2 fifths, times 6 to the 5 halves. Like that. Because, like, that's not simplifying nicely. And just to check, I plugged it in. That's about 10.3216. I do. I would want what's in the box. So if you're going to give me answers, I want what's in the box. If you give me what the decimal, I'll either count it wrong or only give you half credit. Now, test questions would not be that horrendous. Like, they would simplify, and they're made to simplify nicely. So I just wanted to give you an example that snowballed quickly. And there you go. Because as a teacher, I used to teach high school, I'd always hear, oh, you do all the easy ones and then give us the hard ones. You can't say that. That was pretty hard. And I did it. So you have an exemplar of a difficult question. Ask me a question.
How big is this snowball now?
We're done. That's the end of our notes. We're gonna do a lab next. Oh, now if you're talking about the semester, then we can talk about that. All right, well, I'm gonna stop the recording.